Continuing on with this chapter, we talked about intermolecular forces, so forces between molecules, and now let's talk about some of these effects. So one of them is capillary action. Some of these, I see here, viscosity, capillary action, surface tension. So viscosity, this means the resistance to flow. So if maybe you've heard of this before, slow as molasses in January. What does that mean? It means it's moving very slowly, or something's moving very slowly. That there's a very high viscosity. So that liquid has a very high viscosity. And generally speaking, when things heat up, they move more quickly. When they are cooler, they move more slowly. So that's the molasses in January. I know here in Hawaii or in the tropics, but other places, January tends to be cold. So that's the reference to the winter time. I know it's cooler in Hawaii, but molasses is it's still pretty thick, but it's not that much of a difference between June, July, and January. There's the attraction between the molecules in the liquid, and since the attraction, it keeps them from flowing. And capillary action here, so if you want to if you get a prick of blood and you put it on a tube on it, the blood will go up the tube, and it does it by capillary action. And that's also the way our circulatory system works. So we have our arteries, where we have big blood vessels leaving the heart, and then the smaller blood vessels from the arteries, those are known as capillaries. And the capillary action, there's attraction of the blood to the sides of the blood vessels, and that draws the blood away from the heart. And that attraction can be a good thing because it means we don't have to have as high a blood pressure. It can be a bad thing because we can get buildups inside of our blood vessels, which can lead to other issues, of course. But that is part of our circulatory system there, the capillaries that we have. And that's why we call them capillaries, because they have capillary action. And surface tension. So surface tension, this is the attractiveness that things have on the water, on a liquid surface. So if you look here, there's a meniscus, there's water on the left, and you can see a slight meniscus here. I guess it's hard to see in the blue pen. I'll do it in red. So there's a meniscus alongside there. And the reason why there's an attraction, there's actually for silica glass, there's hydroxides on the surface, and there's a hydrogen bond that can happen between water and the surface of the glass tube. So if you have a plastic tube, you don't really see much of a meniscus, for instance, versus like a borosilicate Pyrex tube. And if you see here for mercury, this has so much surface tension, it has kind of a lip there. It always makes me think of one of my favorite movies from my youth, Terminator 2. Good old Arnold, hitting the T-1000. So that was done with mercury. But mercury has a very high surface tension. And if you ever wonder how they make BBs, like the copper BBs, they do that by just simply pouring molten copper. And the surface tension forms spheres. So if you have just a bunch of hot copper, you can pour it, and it'll form BBs of various sizes, and that BB for a BB gun, and it goes and sometimes they splash them in the water too to cool off quickly. We also have insects. I'm from Ohio, and we have these insects. We call them water striders. How many legs? Yeah, it has 6 legs. There's my insect. It has 6 legs, as you can see, and they can walk on water with the surface tension of water. So there's my limited artistic abilities. Okay, so we talked about that the boiling point and melting point is a display of how strongly bound something is. And here shows the vaporization of water. And last semester we talked a little bit about what vapor pressure. Vapor pressure is modeled as a pressure that the liquid puts on the surface. And when the ambient pressure equals the vapor pressure, the liquid boils. But then at a certain vapor pressure, there's a certain fraction of water molecules at various temperature. And that fraction of pressure is the vapor pressure. Where does this come from? That's actually from distribution of energy. So if you see here a lower temperature, higher temperature, it's not really a pressure. We model it that way, but it has to do with kinetic molecular theory. So the red curve, the more broad one, and the blue, the narrower curve there, the higher temperature one has a higher fraction that has enough energy to escape the intermolecular forces, and that's the reason why higher temperatures have more mixtures of has a higher vapor pressure. It doesn't have to do with the pressure that the liquid exerts. Okay, so let's use some of these this energy that it takes to vaporize and the heat of vaporization. So for instance, the heat of vaporization of water is 40.7 kilojoules per mole. Calculate the mass of water that can be vaporized as boiling point with 155 kilojoules of heat. I'll go back to blue. I like blue. So this is good old dimensional analysis. You have 155 kilojoules of heat. So then water is going to be, we have to divide by the heat of vaporization, 40.7 kilojoules. Then water is 18 grams water per mole water, and just like this. And also, you ever noticed, and from the last chapter, you can't forget anything that you learned last semester. You have to keep on going with it. So you can't just dump your brain and say, oh, I'm never going to use this stuff anymore. Guess what? 161 is really a prerequisite for this class, so you have to remember all these. And also you can see here that the units cancel. Kilojoules cancel, moles water cancel, and you're left with mass of water. And the mass of water here is 68.6 grams of water here. So recap with this one using the amount of heat divided by the latent heat. Oh, the heat of vaporization is also sometimes called the latent heat. Divided by the latent heat, and then times the molecular weight of water, we get the mass of water. So another thing with this, the most common mistake I see with students is order of operation. So you may have a smartphone and an amazing calculator, but it's only as good as the human that puts the input. So it can only do what you tell it to do. Order of operations, parentheses are first, powers and logs are second, multiplication, division are third, addition and subtraction are last, and it always goes left to right. So when you put things in your calculator, make sure you put them properly, because if you do the order incorrectly, you get different answers. And this is the most common one. I look at the setup for a problem, and then the numbers are just input in the calculator improperly. So keep that in mind when you do this. So this is for you to try. So heat of vaporization of acetone is 29.1 kilojoules per mole. How much heat is required to vaporize 100 grams of acetone? So work on that, if you will. The answer is D. Okay, so one thing to note here, boiling. Boiling is a dynamic equilibrium, so it's kind of like, it looks like water is sitting there boiling, or here's just water sitting in a beaker. So it looks like it's not doing anything. Actually, it's an extremely complex thing that's going on. The water molecules, they're leaving, they're entering solution, and they're bouncing around with each other. Eventually, they reach an equilibrium, and in the water molecules, some are leaving the vapor phase, some are condensing. Some are condensing, some are vaporizing. So it's a dynamic equilibrium, and this is also true of boiling water. So boiling water, as water is boiling, you have some of the water molecules are condensing back down and also some are boiling. So it is, in fact, a dynamic equilibrium. We mentioned vapor pressure. We also talked a little bit about this in the previous semester, but depending on the ambient pressure, the boiling point is going to change. So at sea level, it's 1 atmosphere is 100 degrees Celsius, but as you go up higher in the approximate pressure, the boiling point of water goes down. So you can see here, depending on where you're at, it does change a bit. So Next thing I'm going to talk about is the Clausius-Clapeyron equation. So this is what's known as a semi-empirical model. So you'll see lots of these throughout your career in science and in engineering. So if you're a scientist and engineer, you will see lots and lots of these semi-empirical models. So sort of empirical. So what Messieurs Clausius and Clapeyron did is they gathered a bunch of data, and they found out that if they plotted the natural log of the pressure in millimeters of mercury versus the inverse in temperature in Kelvin, they got mostly a straight line. And then they model it this way. The slope of the line was then minus the heat of vaporization divided by R. R is the gas law constant. R is also the Boltzmann constant times Avogadro's number. And then the y-intercept is natural log of beta. And so what? Why do we care? What's important right now is this two-point form equation here. And this is how you derive that. So I'm picking P2, just P2, T2, P1, T1. So natural log of P1 is minus delta H over R, 1 over T1 plus natural log of beta. And then I'm going to write P2 on top of that. And now I'm going to subtract the second equation, the first equation from the second equation, and the natural log beta terms go away. And we have natural log of P2 minus natural log of P1 equals minus delta H over R, T2 minus T1. And this ln P2 minus P1, that is P2 divided by natural log of P2 divided by P1. If you remember, these are the natural log identities. If you study this in mathematics, if you haven't, this is now you know them. Natural log of A minus natural log of B is the natural log of A divided by B. Natural log of A plus natural log of B is the natural log of A times B. And also anything to the natural log, e to the natural log of anything that gives the original variable back out. So that is that equation there. So let's apply that then to this equation. So this equation here. So using this to calculate. Let's look at methanol. Methanol has a normal boiling point of 64.6 degrees Celsius and a heat of vaporization of 35.2 kilojoules per mole. What is the vapor pressure of methanol at 12 degrees Celsius? So you have to pick your variables. So I'm going to highlight in yellow P1. So I'm going to call these P1, the normal boiling point. So this is P1, T1, and then in red here, I'm going to have, so this is the vapor pressure there and 12 degrees Celsius. So just make sure you're consistent. You can do it either way. Just make sure you're consistent with what you choose. And with this as well, don't forget that this is in Kelvin. So 64.6 degrees is going to be 285.2 Kelvin, and 12 degrees Celsius is I'm sorry, I got this backwards. This one is 285.2. That's 12 degrees Celsius, and 64.6 is 337.8. 337.8. I'm falling around in the book. So just make sure that you use the proper terms. For me personally, I like doing the algebra first. So how do you solve this one? You take e to both sides, and then this becomes P2 over P1 equals e to the minus delta H over R, 1 over T2 minus 1 over T1. And then now you have to multiply both sides by P1. I'm just going to use graphics. So that just goes over there, and then your P2 is this. So let me move this over. So our P2 is that. Then you put in, I like to do the algebra first, then you put in the numbers. So P1, normal vapor pressure, normal boiling point, I should say this. This is 1 atmosphere, which is 760 millimeters of mercury. So it's going to be 760 e to the minus delta H. So minus delta H is 3.5. I'm going to go ahead and I just put this in joules because I always mess this up on my calculator. Then R is 8.314 joules per mole Kelvin. And the temperature, so T2 is 1 over 285.2 minus 1 over 337.8. Okay, so now also before I put this in the calculator, I like to ask myself, does this make sense? So I look at quantities, and this quantity right here, this 1 over 285.2 minus 1 over 337.8, I look at this number and I know that this number is going to be a positive. This number is a positive number. Why is that? Because 1 over 285 minus 1 over 337, 285 is a smaller number than 337, and then because of that, 1 divided by a smaller number is a bigger number than 1 divided by a larger number. So for instance, instead of this, imagine this as 2 and 3. 1/2 minus 1/3. So 1/2 is a bigger number than 1/3. And so if I have 1/2 minus 1/3, I know that's a positive number. Of course, 1/2 minus 1/3, that's an easy one. That's 1/6, right? So I know that that number there is a positive number, which means this whole number here over the exponents, I know that whole number is negative. And e to a negative number means it's going to be a fraction. And that means that 760 times e to that number is going to be smaller than 760. So if I put this in my calculator, I should get an answer that's smaller than 760. And if I put it in properly. And this makes sense, though, because it's a lower temperature. So 12 degrees Celsius is lower than 64.6. So yes, this is a lower temperature. So then yes, there is a, that makes sense that I have a lower vapor pressure. So you put that in your calculator, and what you should get is 75.4 torr, and torr equals millimeters of mercury. So that's the same units. They don't change. Torr is just some guy's name, if you're wondering. Okay, so recap with this one. We're going to use the Clausius-Clapeyron two-point equation to solve for the vapor pressure at a different temperature, knowing the normal boiling point. Normal boiling point means what something boils at 1 atmosphere of pressure. And 1 atmosphere of pressure is 760 millimeters of mercury. And then we apply the equation here. I do the algebra first. That's my own personal preference. And make sure you're consistent with what your P2s and P1s are, and then you get the answer to be 75.4 millimeters of mercury. So if you're wondering some of these log rules, so here's a review here. Let's talk about exponents. So anything with a 0 power, except for 0 or infinity, is 1. So anything with the first power is itself. Second means you multiply itself by 2. And third power times 3. To the minus power, so 10 to the minus 1 is 1 over 10 to the first. 10 to the minus 2 is 1 over 10 squared, and so on. What a logarithm is looking for that exponent. So log, usually you say log, I mean log base 10. So like log base 10 of 100, 100 is 10 squared. So that means that log of 100 is 2. So it's the inverse of the powers. And likewise, log of 1/100th, so 0.01, that's the log of 10 to the minus 2, it's minus 2. So if you change the base, so for instance, log base 7 of 49, 49 is 7 squared, log base 7 of 49 is 2. What a natural log is log based E. E is Euler's number, Euler's number, whatever you want to say. And also, this is, so you can see here, log of 5, so I put log of 5 there. 10 to that number gives you back 5. So I mean, so I'm just, this just the truncation error, so you can see it goes to 5.00. It's just, the truncation error means the chopping off the end numbers. If you, by definition, that's what the logs, inverse logs are. Same thing with natural logs here. Natural log of 5, e to that natural log value pops it right back out. Okay, so, and if you do this, why don't you try this for yourself, and pause it and try it out. Well, I guess I've already given you the answer. The answer, and using the model, is 27.9. The real answer, so if you actually measure the vapor pressure of water at 25 degrees Celsius, it is actually 23.8. And why am I talking about this? This is just to illustrate to you the difference between a model and real data. So the model predicts it to be 27.9. The data shows it to be 23.8. So I mean, there's error. So when you do a model, a semi-empirical, sort of empirical model, sort of experimental model, there's going to be a little bit of error. And that's part of what it means to be a scientist and engineer, is you have to be able to understand models and the fact there are going to be error, and then you have to manage that error, because your numbers are not going to always be precise. Even by measurement, there's error involved in measurement. So managing all this error and finding out when the error is acceptable and when it's not acceptable is an important part of being a scientist, and also recognizing the limitation of the models that we have and what they can tell us. So that is part of your job as an up-and-coming scientist. So join us next time for the third part of this chapter.